Hi, in this video lecture we will solve this exercise. To linearize, the objective is to linearize this dynamical system, which is x dot is equal to x squared plus u at a point I will explain. Let us brush up what we discussed in the previous lecture. First of all, we introduced Taylor's approximation theorem that we will use here to linearize that dynamical system. So Taylor's approximation theorem states the following. Taylor's approximation theorem, I have written here the theorem for k equals 1. So I am looking for a first order approximation, a linear approximation. States that if a function f is differentiable at the point x0, then we have the following approximation: f at the point x close to x0 is equal to f at x0 plus the derivative of the function at x0 times x minus x0. So this is the first thing that we will use to approximate this nonlinear function. This is a nonlinear function. Can you see why? Because of x squared. X squared is not a linear term. And the second thing we introduced in the last lecture is the definition of a linear dynamical system. A linear dynamical system with state variable x and input variable u is one that can be written like that. This is a linear dynamical system. This is not a linear dynamical system. This is called an affine dynamical system if we have a constant term. This is not what we're trying to achieve. This is what we're trying to achieve, the black equation. So this is from the previous lecture. Just a short revision. And now the exercise is to linearize this nonlinear dynamical system. But the question is, at what point? And of course, at what point does it make sense to linearize a dynamical system? And when we talk about a point, apparently we're talking about the state and the input variables that are involved in that system. But before we go into a mathematical discussion, let us think of a dynamical system. For example, this clapperboard is essentially an inverted pendulum. And suppose that I want to operate it at this vertical position. I want somehow to apply the necessary forces so that I keep it at that upright position. It is apparently this upright position at which and around which I need to gain an understanding of the behavior of my system. So it is around that point where I must linearize. But that point has a particular property which is very interesting. If I just leave it here and I apply just the right force, which is in this case is equal to 0, so if I apply no horizontal forces here, and this is initially at the upright position, it will remain at that upright position forever. Such states and inputs, such pairs of states and inputs are called equilibrium points of the system. Let us write down the proper definition. So the definition of an equilibrium point of a pair x0 u0 is the following. x0 u0 is an equilibrium point of a dynamical system if the state of the system remains at that x0 forever for all t which are larger than or equal to 0. So forever, it will stay there forever, provided that it starts from there and that the input variable is constant and is equal to the corresponding equilibrium value. So in the example of the inverted pendulum of the clapperboard, if the horizontal force is equal to 0 and the initial angle is equal to 0 and the initial angular velocity is equal to 0, this is also a state of the system, then the system will remain here, will remain at that upright position forever. And this is an equilibrium point. Now the question is, in this exercise, how can we determine an equilibrium point for that system given by this equation? We will use now the following proposition. The proposition states the following: a pair x naught u naught is an equilibrium point of the dynamical system x dot is equal to function f of x and u. It is an equilibrium point of a dynamical system given in its state space representation if and only if it satisfies f at x naught u naught is equal to 0. In this exercise, for instance, we have the dynamical system x dot is equal to x squared plus u. Very good. So this function f is apparently x squared plus u. So x naught u naught is an equilibrium point if and only if this holds. For example, substitute here 1 and minus 1, and you will confirm that x0 equals 1, u0 equals minus 1 is indeed an equilibrium point of that system. So now let's write properly the exercise. It will be linearize the dynamical system x dot equals x squared plus u at a point which must be an equilibrium point. And let us take here 1 and minus 1, but you can choose whatever equilibrium point you like, whatever equilibrium point is relevant for your application. And the question is, where do you wish to operate your system? Or around what point do you wish to study your dynamical system? And we have here this nonlinear function x squared. Let us give this a name. Let this be phi of x is equal to x squared. And we want to linearize this function at x0 equals 1. By Taylor's approximation theorem, the derivative is very easy to derive. It is x squared derivative. The derivative is 2 times x. Therefore, the value of the function at x0 is equal to 1. The derivative of the function at x0 is equal to 2. And if we plug in these numbers in Taylor's approximation, we obtain we obtain 2x minus 1. Let's write it clearly once again. X squared is approximately equal to 2x minus 1 for x close to 1. So it seems that our job is done here, because we can take this nonlinear equation. Let me just delete everything. Let me erase everything. So it seems that we can say that the solution is x dot is 2x minus 1 plus u, which in fact is much simpler than the original equation, which involves x squared. This is a lot more linear-ish. Unfortunately, we have ended up with a constant term. But I promised you in the beginning, and in the previous lecture as well, that when we have an affine system, there is a way to introduce a change of variables that allows us to write it as a linear system. The change of variables we will introduce, we will introduce actually variables which are called deviation variables. And we will introduce one deviation variable for the state, which is denoted by x bar, and one deviation variable for the input u bar. And it will be x minus x0 and u minus u0. Now, so this is the linearized dynamics. From here, from this first equation, I can solve for x, and it will be x equals x bar plus x0. Similarly, I can do the same for u, and I can replace now x by x bar plus x0. x0, of course, in this exercise is equal to 1. And then u bar plus u0, so u bar plus minus 1, so u bar minus 1. 2 minus 1 is 1, minus 1 is 0, and overall we have 2x bar plus u bar. Let's write it once again here equivalently. We have x dot. We are almost there. The trick here is to note that if we take a derivative on both sides of this equation, we have, if we differentiate both sides, we have x bar dot, the derivative of x, is equal to the derivative of x here. The derivative of x bar is equal to the derivative of x, but this is a constant term. This is just 1, for example, in this exercise. So x bar dot is equal to x dot, and I can simply put a bar over here. And this is the linear equation, which is a linearization of this original differential equation at x0 is equal to 1 and u0 is equal to minus 1. Let's do one more exercise. Now this is slightly different compared to the one before. Here we need to linearize this dynamical system, x dot is equal sine of x plus u, at an equilibrium point. Not at a particular equilibrium point, just an equilibrium point. What do we know about equilibrium points? We know that they satisfy this equation. We cannot do much after this point, but we can keep this equation. Actually, it will come in handy in just one moment. So this is equation number 1. We cannot solve it. We cannot, specifically, we cannot find a particular equilibrium point. We're not even looking for a particular equilibrium point, but we know that all equilibrium points must satisfy this equation. And then, what is the nonlinearity here? It is sine of x. So let us define a function. Let us define this function phi, which is sine of x. There is no problem with this function. It is differentiable at all points x0. Let us now linearize at the point x0. So we have the function is approximately equal to the value of the function. This is phi at x0 plus the derivative at that point times x minus x0. x0 like that. Superscript. And this is a valid approximation for x close to x0. And this is equation number 2. I can now approximate my nonlinear differential equation by replacing sine x by this expression. And this is equation number 3. This is not a linear system, yet it is an affine system, because if you see here we have this constant term and we also have cosine x0 times x0. But one thing we can do is that we can write equation number 1 just below equation number 3, and this is a little trick we can do. Of course, we can introduce deviation variables at this point, but let us just not do it yet. Let us just copy equation number 1 below equation number 3. Actually, I would like to write it. I wrote 0 on the left-hand side. I would like to do one more modification. Let me write u0 over there. Now, before I just tell you the solution here, let us reflect for a moment and let's think what happens if we just subtract equations from subtract by parts. We see here that x minus x0 is what will become x bar. U minus u0 will give rise to u bar. And then sine of x0 with this sine of x0 will just be removed from the equation. So it suffices to subtract by parts, and I will have immediately the result. So it is x dot is equal to cosine x0 times x bar plus u bar. Now this is a dynamical system with variables x, x bar, and u bar, but we mentioned before that because of the definition x bar is x minus x0, if I differentiate both sides, this is a constant term over here, and I have x bar dot is x dot. So I can simply put a bar here, and now this is a simple equation. It is a dynamical system with state variable x bar and input variable u bar. And cosine of x0 is just a number. It is a constant. Okay, so the solution here is simply, which is in terms of the deviation variables x bar and u bar. And this is a linearization, not specific to some particular x0. Now, whatever x0 and u0 we might have, we can construct the linearization. We can linearize at 0, at 1, 0.5, and so on. So that's it. This is the procedure for linearizing differential equations. So in summary, what we need to have in mind is, first of all, Taylor's approximation theorem with k equals 1. Let me write the equation down once again. The second thing to have in mind is what is a linear dynamical system. The third thing I would like you to keep is the definition of an equilibrium point. Once again, if I start at an equilibrium state and I apply an equilibrium input, I will stay at that equilibrium state forever. This is the definition. And there is also a result here, a very useful result. If this is my dynamical system, then this equation gives me all equilibrium points of the system. And the fourth thing to have in mind is deviation variables. Whenever the system we derive from linearization is not linear but affine, we can introduce deviation variables, and then the system becomes linear in these new variables. So this is a change of variables. Okay, and of course the little trick where we subtract by parts in the last exercise, in which deviation variables just appear somehow, just appear naturally from this procedure by subtracting by parts this equation from the linearization. So this much. Now you know everything you need to know about linearization, at least for systems with one input variable and one state variable. We will discuss later about systems with multiple inputs and multiple states. So that's all for today. Until next time, goodbye.